Hi everyone, as promised, I'll be going through question 9 of the 2016 China Chemistry Olympiad paper. Because I don't have the suggested answers for this paper, I can't guarantee that my answers will be correct, and yeah, so please just keep that in mind, and if you have any correction or feedback, please do let me know, because admittedly I haven't been doing Chemistry Olympiad for a long time, and even back when I was doing it, I wasn't that great at organic chemistry, so please forgive me if I make any mistakes, and please do point them out. So let's begin. So question 9.1, this reaction was carried out under two different circumstances, HCl and K2CO3. So first we have a strong acid and then we have a weak base, and we know that the two different products are obtained respectively. So the other compound B, would then be when this NH2 group attacks this carbonyl. So that will give you your substitution product. Remember your hydrogen. Yeah, because if you think about it, this compound doesn't really look as nucleophilic as this compound. In fact, the compound on the left has two nucleophilic sites, the lone pair on the oxygen and the lone pair on the nitrogen, and both or either can attack the carbonyl group here, making this good leaving group fly away after a substitution, nucleophilic acyl substitution. And yeah, so that's basically what happens in the mechanism. So the question we have here is why A is obtained under acidic conditions while B is obtained under mildly basic conditions. Well, we know that NH2 is not only a strong nucleophile, RNH2 is not only a strong nucleophile, but it's also a strong base. So this strong acid here is obviously going to protonate not only your carbonyl group, carbonyl oxygen here to act as a catalyst, but it's also going to protonate this NH2 group here. This is why you can't form an amide with carboxylic acid and an amine. So this is what I mean. So RNH2 plus, let's say, your carboxylic acid wouldn't give you this is not possible, this reaction, because even a carboxylic acid is enough to protonate this, and it will instead give you the salt, because protonation is really fast, and so this reaction will predominantly occur, and that is why this the first reaction under acidic conditions can only give you the salt. So after you protonate the NH2 group, if you have your HCl that is not very concentrated, and so you will have sufficient OH groups to still react, and so that will give you this compound. And you can check the pKa values for these two groups, and you will see that NH2R is a much stronger base than alcohol. So yeah, that's why this gets protonated first. Now, under basic conditions, obviously this protonation doesn't occur. So we know that NH2 is a stronger nucleophile than OH. So this is going to be the one that attacks the carbonyl group, causing the substitution to occur. Yeah. Okay, now we are going to see why. Yeah, we have answered part 2 of the question. And why does A convert to B upon the reaction with K2CO3? So that is again because you have your K2CO3 will just help remove the extra proton here, so this becomes 2, and then you have this thing which obviously isn't very preferred because your NH2 is stronger than your OH here, so it was simply, this end will simply attack here, and you have an internal substitution. And this is possible because you have 1, 2, 3, 4, 5 things in between, so the intermediate is going to be a 5-member ring. So that is possible, that is certainly possible. And so the kinetics barrier shouldn't be that high, and your final product is more stable. So yeah, compound B will be preferred. Okay. Yeah, let's take a look at 9.2 now. So 9.2 is the question that I have to actually search up online. It is also something that I'm not very familiar with. So what happened here is an SNI type reaction. So that's an internal substitution. So the reason that we don't get compound C is because something else happened, as the question said. So the first step of the mechanism is the same, because like you have a nucleophile here, you have an electrophile here, so that's probably the only way that the first step can take place. So the first step is going to be something like this. You have your R group here, then you have your O here, and you know that the lone pair is going to be coming up. So you will have your S, O minus, you have your Cl, you have your Cl. But in this case, rather than expelling the Cl and then letting the Cl attack here, like letting the expelled chloride attack there, what's going to happen is that instead you have a you can form a transition state that is favorable, because so you can have this chlorine attack here, giving you this outcome. So that is because you have your 1, 2, 3, 4, 5, 6, 7. So that is kind of a 7-atom ring that's formed in transition state, and so this whole chain is long enough to wrap around and attack from there, and so the product you're going to get is this. Oops. So the chlorine will instead be here, and oops, I am missing something. Oh, sorry, my apologies. I was wondering how, yeah, my arrow pushing was incorrect. The double bond shouldn't be there. The double bond is up here. So that's our compound, this compound. And so yeah, that explains, I was wondering why a 7-member ring would work. Yeah, so instead the transition state is a 6-member ring, which is much less strained and much more preferable, which is why this would happen. So please allow me to correct myself. This is our atom 1, atom 2, 3, 4, 5, 6. So that is a really, really favorable transition state because it's really stable, and that's why this wrapping around the chain is long enough but not too long that it gets all tangled up and strained. So that is a really favorable transition state, and that's why the kinetics barrier for this transition state is lower, arguably lower than if you have an if you have a normal SN2 reaction. So that's what's going to happen, and then you are going to get your product. So this is your intermediate D, and then you will have your stable 6-membered ring transition state. And so after that, you will have your compound E. So that is this compound, it's compound E. Let me double check so I don't accidentally embarrass myself again with this. Yeah, so that should be your compound E. Let's see whether the methyl group should point this way or that way. So we need to take a look at the stereochemistry here. And given the difficulty of this paper, I think the stereochemistry is marked and something that's quite important. So just to make it very clear, let us redraw our intermediate D. So we're not going to care about this part, so I'm just not going to draw that part. So when this R rotates up, you have a H here. So first the H becomes a solid line, and then the H will point out. So when your R is here, your O will be behind, and then you will have your sulfur here, O minus, you have your Cl, Cl. So we see that when this happens, this methyl group is pointing there. So my first initial deduction of compound E is in fact incorrect. So that should be the structure of compound E. It should be that stereoisomer. So yeah, just checking whether you're watching, huh? No, I'm kidding. I didn't know that this would matter until I drew it out. So it's always important to check your answers, I guess. Now, okay, so in the next part, in the following reaction, so let's draw the 3 isomers first, because we know that the ending product will contain a carbon-carbon double bond, and we know that the group that's reacting with your SOCl2 is this alcohol group here. So we know that a double bond is to be around there somewhere, and it's a carbon-carbon double bond. So that doesn't really leave us with a lot of choices. So let's just draw out all 3 compounds first, and then we can label them with their respective letter. Anyway, the question is asking us to do that. So the first structure is, of course, when a double bond is formed here, and then you kind of have this. And then your second possibility is this one. So this still retains its stereochemistry here. So this is your second option. And your third option is going to look quite similar to your first one. So these are your G, H, and J, and one of it isn't formed. So we're just going to decide which one isn't formed. So we see that if we basically replace this OH with a Cl, so if this thing undergoes an SN2 reaction, Then you're going to have this, and you're going to have the Cl pointing out. And now the Cl group has to leave. And so if you want an E2 reaction to occur without, having a carbocation in pyridine, which doesn't really seem too stable because it's kind of basic, you need to have anti-paraplanar geometry for E2 to occur. So the geometry is actually set up for you. So this H and this Cl is anti-paraplanar to each other. So this reaction can occur. So the elimination can occur, kicking Cl out. Now the one, yeah, so my worry here is that if SN2 reaction has taken place, then there isn't really a reason of explaining why one of these molecules wouldn't be formed. So I guess we have to go back and adjust our assumption that SN2 has taken place between the alcohol and the SOCl2. So from previous part, from 9.2, we know that SNI can also occur with the retention of stereochemistry because it is kind of internal, so it didn't, nothing kind of kick the O out through a backside attack. So if there were no double bond, then the stereochemistry of the new Cl would be in the same configuration as the OH. And so we can probably assume that an SNI reaction occurred with a retention of stereochemistry. So this is going to be your chlorine, and this is going to be your methyl group. And so we see that this chlorine here and this hydrogen here, they are no longer antiparaplanar, and that means that this elimination cannot occur, and therefore this product is not formed. However, the hydrogen here, as well as the hydrogen on the methyl group, they can be in antiparaplanar geometry with the chlorine here, and so an E2 elimination can occur. And that is why this is our product J, and that is not formed in the above reaction. And these are G and H. And as the question didn't provide us with further information, we can just label any of them G and the other one H and take our marks and run. So yeah, so I didn't really work through the solution before doing this video. So as you can see, I also struggle with this kind of questions, and I imagine that in competition, under competition, the stress of competition and everything, it would be more challenging for people to solve. But so it's okay to initially get an answer wrong and go back and change something in the competition. You just have to adapt to the question and just don't really assume anything. I guess that's the takeaway point from this. And also don't give up, because if you can't do it, you can make a guess. And yeah, so I guess that's all I have to say for now. I'll see you in the next video. Good night and goodbye.